Three, two, one. Well, good evening, and my name is Curtis Brown. Welcome to Monday Night Calculus. This is the second to last, I think, or third to last session of the season. I can't remember where we are, even what day it is. We've just gotten done with a whole bunch of conferences and things, and we're back now, settled in our respective homes. I'm joined once again by Steve Kokoska and Tom Dick. Really excited to have you guys here this evening. Just in case anybody is wondering, that is not a halo behind my head. It is a picture of the solar eclipse that happened just about a month ago up in Oregon. Of course, it happened across the United States, but Oregon is where I happen to view it from. If you've got a chance, go ahead and put a question in the chat. Drop us a hello, and I'll make sure to try to pass those things on to Steve and Tom as we go through the session this evening. One other thing, if you stick around towards the end, I'll go ahead and put my email address in here. So teachers, you can get a professional development certificate for hanging out with us this evening. And finally, just go ahead and use this with your students. We really encourage, Steve put some time into writing those questions. Steve and Tom put some time into those questions, and really, the kids benefit from the ability to have these questions early and then being able to come in and check these things out. So I highly encourage you guys to do that. I know there's several folks out there, so be watching for those questions in the chat, and I'll turn it over here to Steve.
Terrific. Thank you very much, Curtis. It's wonderful to be back again with both you and Tom. I've forgotten, Curtis, did you do your homework for tonight?
Oh, that's the other thing. Yeah, that's right. I was supposed to put out a plea to the people in the chat. I did not do my homework tonight, so please be on the ball answering questions. I know that Wanda will be out there answering questions for me. Hopefully there will maybe be some others to help me out. Mike Houston is going to be in the chat helping me out, and I know that, so that'll be good.
Okay.
Have a little bit of extra help.
Very good. Well, Riemann sums, Curtis, is one of my favorite topics. And as Tom and I would both attest, there are generally questions about Riemann sums on the AP Calculus exam and frequently on the free response portion of the exam. I think we've assembled some good questions tonight. We've got a couple of interesting, I think, overtime problems too. Some with technology, some that we might do by hand, and I think a lot of visualization. So there's some good problems here, I think, that you can do with your students. So in this first one, fairly straightforward, not contextual. We have a table of values. We have a table of some values of f over the interval 0 to 20 using some selected values of x. And what we'd like to do is to find a left Riemann sum for f over the interval 0 to 20 using as many subintervals as possible. A couple of little things. Again, this is a common problem that we might see on the AP exam, perhaps not with as many subintervals, but this type of problem I think is very common. And this language here, I kind of like using many subintervals as possible, but frequently on the exam, it says something like, help me here, Tom, using subintervals as determined by the table. That might be a little bit more ambiguous, but that kind of language is also used. So, all right, we want a left Riemann sum. So we're going to divide this interval up 0 to 20, 0 to 2, 2 to 5, 5 to 9, and so forth, 9 to 15, 15 to 20. One thing you should notice here right off the bat is that these subintervals are not of equal width. That's one thing that students often miss under the pressure of the exam. Trying to do this very quickly, they just quickly assume that the intervals are all the same width. They're not here. We want a left Riemann sum, so I'm not going to go through all the details here. Remember that we do provide this solution sheet. We're going to go into this first subinterval, and we notice that that has width 2 minus 0. We want a left Riemann sum. So we're going to evaluate the function at the left-hand endpoint of that first subinterval. So I'll write that to start out with as f of 0 times the width of that interval. In the next interval, 5 to 2 or 2 to 5, excuse me, the width is 5 minus 2, and we want to evaluate at the left-hand endpoint. So that's f of 2. And on, all the way up to the last subinterval, 15 to 20, there's the width, and we want to evaluate at the left-hand endpoint of that subinterval. Let me just note that often in these kinds of problems, they're worth 2 points. And the first point is generally for the form of the left Riemann sum. What does that mean? Well, we're looking for a sum of products. In this particular problem or solution, the way that I've written it, the student would probably receive 1 point for that line because that represents the form of the left Riemann sum. However, in this next line, where I actually go to grab the value at each left-hand endpoint of the subinterval, as I write that line, that would actually be worth both points. So I'll just put a 2 with a circle there. Remember that final numerical answers do not need to be simplified. And so that's the correct numerical answer. And it indicates the form of the left Riemann sum. I'm going to come back there, Tom, don't let me forget this. I'm going to come back to that issue in just a second. So I did all the multiplication, and I got a final answer of 20. And you know me, Curtis, I like to have a visualization here. And so I just sort of drew a graph that went through all of these points, a smooth graph that went through all of these points. And this is an example of this visualization of this left Riemann sum. I go into the first subinterval, I evaluate the function at the left-hand endpoint, and I draw that rectangle, and I find that area. In the second subinterval, this rectangle is actually below the x-axis, contributes a negative value to this sum, but that's the visualization, and on and on. Before I go back to this line, I'm sorry, Curtis, I have to ask you one question here. So this answer of 20 that we got for this left Riemann sum, coupled with this visualization, I'm trying to set this up for you. Can you explain to me, what does that 20 represent? Sometimes we ask students on the exam to interpret their answers. What does that 20 sort of represent? You're on mute, Curtis?
Yeah, I did that so somebody'd have some pity on me whenever I went to try to answer this question. So it's an approximation, right, of the area between that graph and the x-axis.
It is indeed an approximation.
The total area between.
It is indeed an approximation. That's very good. I wasn't thinking of that one, but that's very good. Given the visualization, the graph that I've drawn, can you give me another idea about what that 20 represents?
I don't know. Is this a contextual problem? No, it's not.
No. This is what perhaps if I had used different colors, what I was trying to get at it is the area of these rectangles that are above the x-axis.
Oh,
minus
the ones below it. I'm sorry, I wasn't following what you were asking me there, Steve. I'm sorry.
Okay, it's late.
I want to go back.
I want to go back here. I want to go back here to this line just for 1 minute and talk again just briefly about the grading of the exam. Once again, in these types of problems, what we're looking for are a sum of products. In this particular problem, let's see, there are 5 products. There are actually 5 products and 10 terms. So if we were to give this on the exam, we were looking for those 10 terms. Now, an issue occurs sometimes when these products are very easy to do in your head and students skip a step. And especially if there's one of these widths or one of the values is 1. So for example, let's just suppose in this last one, I don't know, the left hand evaluated at the left-hand subinterval, left-hand endpoint of the subinterval was 6, but the width of the subinterval was 1. This is a tough one. We'd really like to see the student write that 1, but we understand that they might not, because it's very easy to see 6 times 1 is 6. I don't need the 1 there. So just as a word of caution, as you prepare to take the exam, we're really looking for the sum of products. And I would suggest to you, you write out each one of those terms in each one of those products, even if it is a one. If I were telling you about test taking tips, tricks, techniques, don't simplify from here unless it specifically asks for it. That answer right there alone gets both points. That was way too much probably on that, Curtis. I apologize. I think
That's all right.
Tom has a little bit of technology on this, and then I'll come back to number two. Is that correct, Tom?
Yeah, sounds good, Steve.
Okay. I'll stop my share. There you go. All yours.
All right. Okay, so I'll share my screen and pull up the TI-84
Okay.
later
Sounds
here.
good.
And you can let me know if that's showing up okay for you
It
guys.
is indeed. Looks good.
All right, fantastic. Okay, I think I remember recently, Steve, you and I were looking at problems involving approximating the derivative using tables of values. And now
Yes.
we're basically looking at a problem where we're approximating a definite integral value using a table of values. And so I wanted to go back and look at some of the functionality on the 84 that's really handy for that. And that's under the list or stat editor, where we have something that kind of resembles like a spreadsheet, except it's organized as columns of lists. So I'm going to go to stat, and I'm just going to hit that very first thing there, edit. And here's where I've got all my lists. And you can see they're all blank right now. And what I was going to do is just go ahead and enter this table that you were just looking at into the two first columns here. So your table was listed in rows. So I'm going to switch it over to columns.
Okay.
So I'm going to enter my X data here. Let's see. So I'm just copying this off your table. So it looks like it was 0, then 2, 5, 9, 15, and finally 20. So there's my X values.
Okay. Got him.
And now the corresponding Y values, I'll go over to the next list and enter those. I think that's 3, and then a -4, 2, -2, 6, and finally a -5 for that very last one.
Right.
Okay. So in that Riemann sum that Steve calculated, he was doing a left Riemann sum. And one of the calculations he needed to do was the width of each of the subintervals that were determined by the data. Now, our X data, that's in L1. So what I need to do is actually, what I'd like to do is get a list of those different subinterval lengths. So from 0 to 2, 2 to 5, and so on. And I'm going to put those into L3. So I'm going to actually go up to the very top, L3, and define this list in terms of a calculation of the successive differences in those L1 values. And those are my X values. Now, where I can find that is if I go to the list menu and go over to operations, OPS. You look down there at number 7, there's that delta list. That's the one we want. This is going to get our delta X values. So I'm going to do delta list of L1. So it's a second shift of 1. And let's calculate that out. And it should populate that list. Now, these are all values we can kind of calculate pretty easily in our head. And so we could have entered it that way. But if you had a longer list and the values were messier, like decimal numbers, this could be really quite handy to get all those subinterval lengths. So let's just do a reality check. So from 0 to 2, that's length 2. 2 to 5 is link 3, 5 to 9 is 4. This is looking really good. Okay. So now we want to do that Riemann sum. And I'll do the same one Steve did, a left Riemann sum. So let's see, that would be the left endpoint of each interval. And pretty much that's all the values in our second list here, the L2, except we won't use that -5. So that's the one that we won't use. Now, conversely, if we were doing a right Riemann sum, we would use all the values except the very first one. Okay. So I need to actually make a list. I'm going to go up to L4, and I'm going to make L4 equal to L2. And that might seem kind of crazy, but what I'm going to do is edit it slightly. I'm going to go down and just throw away that very last entry, because we're not going to use that 5. We're only using the left endpoints. I'm going to delete that -5. And now my list L3 and my list L4, they both have exactly 5 elements in them. The L3s, those are my delta X's, and my L4 are the function values at the left endpoint of each of those intervals. So we just want to do a product and add those up. So first I'm going to compute the products just going across. And what's really kind of cool is we can do that very easily by just making L5 equal to the product of L3 times L4. And again, we can do a little reality check here. Let's see, is that making sense? 2 times 3 is 6. 3 times -4 is -12. Looks fantastic. Again, these are all computations that are really quite simple arithmetic-wise. But if these were a longer list and more complicated values, this would be super handy for doing these calculations. Now, the final answer would be to add up these values. And again, that's something I could do with paper and pencil quite easily here. But just want to show you how we could add up all the values in a list to get that grand total, which would be our Riemann sum. I'm going to go back to the calculator and bring up the list menu again. Oop, there we go. And under math, you go down to number 5 there. It says sum. That's where you can sum up the entries in a list. And I think all our products were in L5. So I'm going to bring up L5. And now we'll just sum those up. And if I remember correctly, I think you ended up with 20 for a final answer there. Let's see what comes up here. How's that look?
Very good.
Excellent. All right. So again, I'm just going to go back to that editor just one more time. And I'm going to go back to L4. If you were doing a right Riemann sum, you can make your L4. So our original function values were in L2. So I'm going to put in L2 again. Okay, so this is just a copy of all our function values. If you were doing a right Riemann sum, you would start with -4 and go up to -5. The only value you would not use would be that 3. So we can just edit this by throwing away that very first entry. And then we could recalculate L5 to be L3 times L4 again.
Mm-hmm.
And now those are our right Riemann sum products. We haven't added them up yet, but you can see how easily you could do both a left and a right Riemann sum in this way. So I'll hand it back off to you, Steve, unless there's comments you want to make or look at.
There was just one comment. First of all, a couple of folks didn't know anything, had never seen that delta list command.
Yeah, it's pretty handy. Yeah, for
Kudos
Rick
on that
too.
one. That's always a cool one to come across. And then the other comment was that you could also stay in the list and use that command that you did on the home screen at the top of list 6 and just get that one statement in the first element of list 6. That would also
Nice. Yeah, that's similar to how you work with a spreadsheet. Sometimes you'll go over to a new column just to do a single computation, and
sure.
yeah. So that's a nice suggestion. Yeah, I like that.
Yeah, you could totally do that. So.
Okay, I'll do a stop share and hand it back over to Steve now.
Okay, here we go. So, Tom, one thing I would, two things perhaps I would comment on is that the stat list editor, I think, is a wonderful feature. But we should remind people that that is not dynamic like, say, the TI-Nspire. When you change that one column, I guess it was L3 or L4, the remaining columns did not change, even though you had defined them previously. You have to go back and, as you said, recalculate them. So
but he could have stored those equations so they would be dynamic. Maybe Tom will show us a quick demo of that here in a minute. The hard part is with the deleting off a value out of the list.
Gotcha.
That would not be dynamic, but the multiplication, finding the areas and things, you could totally make it dynamic.
So if you have one column that is one element longer than the other and you multiply the two, does it give you an error message or does it just return?
Yeah, it does. It'll complain. It'll actually say something like a dimension error, and that just means that the number of elements isn't matching up in a way that it can make sense out of.
Yeah. Okay.
Oh, here's another suggestion, and Tom, I hope we're not spoiling your
no, it's fine.
But there's another thing that came up in the chat. Midpoint would also be kind of slick to do.
Sure.
You could get in there. You could take you have L3 and maybe divide by 2. Is that what you might do there?
Yeah, I think there with a table where you don't have equal delta x's, you'd have to be real careful that you actually have access to the midpoint of each.
Yeah, that's a good point. Yeah.
So midpoint you can do, but you've got to really be careful with the spacing. Make sure your delta x's are of the right. They don't have to be uniform, but you'd have to make sure you actually have data for the midpoint of each interval that you're using.
That's a good point. Unless you had equivalent intervals.
Yeah, and sometimes we have things where we have the delta x is exactly the same for every every x value in the list, and so then it's quite easy to do.
Yeah, I love it.
So one other comment, just an observation, that when I see something like that on the stat list editor, I immediately think about coding. And could I write a program that could do, left, right, Riemann sums for an arbitrary function and for an arbitrary subinterval width? And we'll get there, I know, but we're doing a lot. I know, Curtis, you're doing an awful lot with coding. And so that sort of whets your appetite a little bit, I think. All right, well, let's try another one. I think this is a nice problem, too. This one relies upon a graph of a function. If I've drawn this correctly, it's gone through some good points. So let's see. We have the graph of this function f that's shown in this figure, and we're going to estimate this definite integral from 0 to 10. We're going to use 5 subintervals, and I didn't put this word in here, but I suppose I should. 5 equal subintervals. And we're going to do a right Riemann sum, a left, and a midpoint sum, and we're even going to try a trapezoidal sum. This is kind of a neat trapezoidal sum, I think, because it isn't one that you frequently see, I think, in textbooks and written literature. And this will illustrate some neat stuff, I think. So, all right, a right Riemann sum of 5 subintervals. All right, so my graph, I'm sorry, Curtis, is going to get a little messy, but we're going to go 0 to 2, 4, 6, 8, and 10, 5 intervals, 5 subintervals of equal width. And this is a right Riemann sum, so all right, we have to go into each subinterval, take the right-hand endpoint, go up to the graph, draw the rectangle, there we go, and find its area. So all right, here's the mathematics, here's the visualization of this as I arrow down just a little bit. First subinterval, well, they all have width 2. take the right-hand endpoint, evaluate the function. How did I evaluate the function here? I looked at the graph. It seems like on the AP exam, we've had a number of these kind of problems lately. We have to read this sort of information from the graph. And so there are my products, giant sum, and I got a value of -2 for that right Riemann sum. And Curtis, the visualization here is given. What does that -2 represent? Well, in this case, the area of these rectangles below the x-axis is actually greater than the area of those two rectangles up above. Okay? Cool. Let's do a left Riemann sum. Here we go. We're getting the idea of this now. We go into each subinterval. This time we take the left-hand endpoint. Here's the first rectangle. The interval or subinterval is 0 to 2. The value of the function is down there at -2. There's my first rectangle. So my first quote-unquote area is -2 times 2, the width of that subinterval. And you know, and some students who do a problem like this on the exam, of course, recognize that there are equal subintervals and will, of course, factor out that width of 2, and that's fine. That's fine also. I added all that up, and son of a gun, I got a 0. Kind of cool the way that this worked out. Good problem for tomorrow morning at 8 o'clock with your class. What does that mean? Well, the area of these two rectangles above the x-axis is actually equal to the sum of the areas of those three rectangles below the x-axis. Pretty cool the way that worked out. And how about a midpoint sum? Let's see. Well, this time we've got to go into each subinterval. Let's do the first one if I can. 0 to 2. Oh, wait a minute here. I have to evaluate the function at the midpoint. Where did that rectangle go, Curtis?
Well, it looks like it crosses at 1. So
right.
the value of the function at 1 is 0, which means your midpoint has a value of 0, which means you have 0 times that interval.
So there is no rectangle there. Very good. That rectangle has no height. Very good.
Look, very see, good. You got me one I could do there, Steve.
So the same sort of thing happens over here, I think, on this subinterval.
It does.
It does indeed. So that's why there are only 3, I guess, visible rectangles here. But son of a gun, these 3 rectangles, or the areas of these rectangles, also cancel out and leave me with a 0. Let's take a look at one more associated with this problem. Well, I think I got to go to the next page. There we go. So this is a trapezoidal sum. Now, I did a little bit of factoring here. Remember the area of a trapezoid? Let's see, 1/2 the height times the sum of the 2 bases. Now, I purposely didn't draw in each of these trapezoids. I'm going to try to draw one of them, and Curtis, I'm going to need a little help here. Let's look at this first area of the trapezoid here, which will include those 4 values, I think. So 1/2 the height. The height is actually the width of the subinterval, 2.
Yeah.
And where are the 2 bases? Well, one base here is actually the value of the function at the left-hand endpoint, which is -2.
Yeah.
And the other base is the value of the function at the right-hand endpoint, which is over here.
Looks like 3.
Looks like 3. So this is kind of an odd-looking trapezoid, but if I draw it, I think it's like this. And so if I do this calculation, see if I've done this correctly here. Well, this 1/2 times 2 just gives me a 1 conveniently. And so this calculation is 1 times, let's see, a -2 plus 3, a 1. It's just plain old 1. So Curtis, for 25 bonus points, what does that 1 represent when I look at this trapezoid determined by that first subinterval?
Well, I suppose if you think about it, it's the amount greater that upper chunk of that trapezoid is above the axis than the lower chunk is below the axis.
Very good. And in fact, that upper chunk and lower chunk have a special name geometrically. What kind of figure is that?
They look like triangles to me.
Very good indeed. So the area of this triangle is 3. The area of that triangle is 2. Subtract them. There's our 1. And that's exactly what's going
Wanda
on.
says I should have used net height.
Oh, that's kind of cool. I like that. Yeah, very good. So I think that answer works out to be a -3. And that's a good problem with nice 4 parts for tomorrow morning at 8 o'clock. Good. I'm going to do one more, I think, and then I'm going to pass it over to Tom for a little bit more technology. So I don't know if we would see anything like this on the AP exam, but these are kind of neat problems, I think, to perhaps think about what an antiderivative would look like and evaluating that antiderivative at the upper bound and the lower bound. Now, I picked a couple of functions that don't have easy antiderivatives, but that's a sort of a problem that you might think about. So this just says use a midpoint Riemann sum with n equal subintervals to approximate each one of these definite integrals. So here's my first one, and I wanted to try to use n equal to 10. Well, I got an m sub 10 if that notation is okay, a midpoint sum with 10 subintervals to be 1.790 roughly. We usually use 3 digits, to the right of the decimal. And so I think I usually round a little bit, I think, when I do that. Why did I put 1.79? I'm going to have to check that. I have a 1.7823 here as the, oh, I get it, because that's the pretty much close to the exact answer. That's what I wanted to show. So here's the visualization. I was able to draw that, I think, with Mathematica. Here are the 10 equal subintervals. And if you were to look at the area of all of those rectangles, there's 2 real skinny ones in there. I think if you add all of those up, you get a 1.79 and pretty close approximation to that definite integral is 1.78. That's pretty good with only 10 subintervals. That's really pretty nice. So let me show you one more, and then I think Tom will show you a little bit more technology. I'm going to arrow up a little bit. Here's another one where I want the definite integral from 2 to 4 of e to the square root of x divided by the log of x. I'm not sure I could find an antiderivative of that. And this time I'm going to try n equal to 20 subintervals, equal subintervals. Here's a visualization. I think I've got 20 rectangles in there, very skinny, tall rectangles. And when I did all of this with Mathematica, I got a 10.58, and son of a gun, look at that. When you get a good approximation to that definite integral, it is indeed 10.580, 10.581, rounded to 3 decimal places. That's really good with just 20 subintervals. Gives you some idea of how powerful that midpoint sum is. And of course, this approximation is very dependent upon the nature of the function, how steep the curve is, and that sort of thing. But that's pretty good in those 2 instances. Tom, a little bit of technology with this one?
Yeah, I think so, Steve. So I'll give it a shot here.
All right, all yours.
Okay. All right, so just firing up my 84 emulator again.
Okay.
Hopefully you can see that. I'll just quit out of this list thing and clear this out. Okay. So Steve, that last problem you were looking at, there you had a specific function that you were computing, your integram function is what you were computing your Riemann sums for.
Yes.
And I wanted to take a look at how you could do that. Now, there's a number of programs out there that people have written that much like what you were indicating, Steve, to compute these Riemann sums. But I do want to show people how you can do that pretty simply without a program, and it's really pretty powerful. So okay. I'm going to take a really easy integral to illustrate this. So I'll tell you what, first of all, let's just do an integral that we could do in our head. I'm going to pull up the math menu and look down there at number 9, FN int, okay. All right, and let's suppose I was integrating from, say, 1 up to 2. Oops, I went a little too far. Here we go. And I'm going to integrate y1. Okay, y1, I'll show you. y1 is actually equal to x squared. And I'll show that to you in just a bit. But let me just go ahead and pull it up here. Integrate that with respect to x. So if y1 is equal to x squared, you can think through what should this really be. So using the fundamental theorem of calculus, we should get, what, I guess x cubed over 3, evaluate at 2 and 1, and subtract. So I think we'll get 8/3 minus 1/3. I think we should get 7/3.
Okay.
I'll buy that.
There we go. And let me just show people there was no smoke here. In my y1, there it is. There's the x squared. So that's all I was doing, is just integrating x squared. It's a very easy one. But I wanted to show folks how you can do a Riemann sum and how you can do it really quite generally. So you can change functions, you can change limits of integration, and not have to do a lot of re-editing to do that. So let me just go through that quickly, how you can do that. So let me quit from the y equals menu. And first of all, let's go ahead and store our limits of integration in A and B. So I'm going to store 1 into A. And then I'll store 2 into B. And so what I want to do is I want to do once I have those 2 limits of integration in there, I want to do a left Riemann sum for y1 from A to B.
Okay.
And I need to know, you can give me any number of subintervals you want. We'll do equal subintervals. So I'll tell you what, I'm going to try 20. And I think I hit the store twice there. So let me back up, delete. And I'll store that in N, which is a pretty popular letter for our number of subintervals. Okay, so I've got limits of integration are A and B, 1 and 2. We're going to do 20 subintervals. And now I'm going to go to the list menu again. And I'm not going to go into the editor. I'm going to go straight to operations. And if you look down there at number 5, it says sequence. So I'm going to hit 5. And I've already entered into, so we could enter this right in here, a sequence that's going to represent the individual products in a Riemann sum. So you notice there's y1. And I've got A, that's my left endpoint of my interval, plus K times, now I've got this interesting thing. It says B minus A divided by N. What is that? Well, that's just my equal length subinterval length. So I took that would be 2 minus 1 divided by 20. So that'll just work out to be 1/20th. But notice that as you update the A and B in your N, this will be calculated for you. So this will always calculate your delta X. And so I'm evaluating Y1 at A plus K. Now, K is the variable in the sequence that'll run from 0 up to N minus 1. So that'll be the left endpoint. So when K is 0, I'll just get Y1 of A. When K is 1, I'll get Y1 of A plus 1 times my delta X, and then Y1 of A plus 2 delta X, and so on. So this will give me each of my left endpoints evaluated. And then over here to the right, you can see I'm taking each of those times, and you can't quite see it. When I paste it into the calculator, you'll see I'm multiplying by delta x again. So there's a b minus a over n here on the end. Let me just scroll over there so you can see that. So that's evaluating each of the function values at the left endpoint of each subinterval, and then it's multiplying each of those function values times the delta x value. And it's going to give me a sequence of those. And so let me just go ahead and paste that in to my calculator. Boom. So we got this really long thing here, and I'm going to go ahead and enter that. And what I've got now is a list of the results of each of those products.
Mm-hmm.
And so one more step here is I need to add them all up, and then that'll give me my Riemann sum. So let me go back to the list menu again. And go to math. I want to do number 5's the sum. And it's the sum of that list that I can see there. So it's the last answer that I got. So I'm going to do second answer here. There we go. And it should give me something relatively close to 2.3333. So let's see how good we did. Not too bad. Okay. So that's an approximation. And what's nice about this is I could change this to a new function. So for example, we could put in, say, 2 and store that in for A. And we could take 4 and store that in for B. I'm going to leave N as 20.
Okay.
And then I'm going to go to my Y equals menu, and I'm going to put in the function that you were last looking at, Steve. I think it was it e to the square root of x?
Correct.
Over ln of x? Okay, so let's do that. Oops, I get rid of that 2 up there. Let's see. Oh, you know what? I'm going to just clear this out and try that again real quick. Okay. My apologies. There we go. So e to the square root of x.
While you're typing that, Tom, there was a comment in the chat about how great this connection is to be able to see between this and the limit or sigma definition of definite integrals, section 6.3.
Oh, right. Yeah.
The CED. So
okay.
Cool connections here.
Okay, so here's this kind of nasty function, e to the square root of x over ln of x, and this would be pretty hard to anti-differentiate. So here's my y1, and if I go back to the list menu, oh, excuse me, let me quit out of that first.
Go to the home screen first.
Yeah, I want to go to the home screen first. That's right. Thank you, Curtis. That's it. I've made that mistake before. Okay, so now I'll go to the list menu. Otherwise, it would have put that into Y2 for me. And we'll do a sequence. And notice that the sequence I had in there before is still there, but I've already redefined Y1. So this is that new function. I redefined A, I redefined B. I think we left N as 20.
Mm-hmm.
And so this is going to do a left Riemann sum for this new function from 2 to 4 over that interval. So let's give it a shot and see what we get. Now, midpoint Riemann sums, Steve hadn't mentioned this, they're often the best choice. If you've got a choice, they're often the give you a better approximation than left or right. But one advantage I have here is I have more subintervals than Steve used. I use 20 instead of 10. So it'll be interesting to see how this one compares to the value Steve got. So let me enter that in. And then we'll enter again to get the actual calculation. Now this is calculating all the individual products. So we still need one more step, and that's going to be to sum it all up. We'll do the sum of that last list here. And Steve, let's see, I think the answer you got, the approximation you got was like 10.58.
10.
It was really, really close to the actual value. So I'm guessing this won't be quite that close, but we're hoping it's pretty close to 10.58. Not too bad. So I'm off by 300ths, but pretty darn good. And
good.
And what's really nice is that you might look at this expression and say, well, that's pretty long, but that is the expression for a Riemann sum, and it's updatable very, very easily just by updating the value of a, b, and your function y1. You can do a huge number of these. Also, I'll just very quickly go back to that that sequence thing. I did want to point out one last thing. If you wanted to do a right Riemann sum instead of a left Riemann sum, you would have this exact same expression, except you would start at 1 and end at n. So that would give you the right endpoint of each of your subintervals. And if you wanted to do midpoints, what you could do is have k run from 0 to n minus 1, but replace k in here by the quantity k plus 1/2. And that would hit the midpoint of each subinterval. So it's really cool. So there's not much you have to do to tweak this to get a lot of different Riemann sums. Okay, Steve, I'll stop there.
Okay.
And turn it back over to you.
Okay. Here we go. Beautiful. So in this number 4, we're kind of working backwards a little bit, I guess. We want to express each limit as a definite integral. I'm not sure exactly why, Curtis, but a number of my students have trouble with these types of problems. It's perhaps because we don't do as many of these by definition sort of problems anymore. But these types of problems appear on the multiple choice portion of the exam. They're still there. So students need to be able to do this. Now, I have sort of my own kind of weird way of attacking these problems. Let me scribble a little bit down at the bottom. I just want to remind myself here that this definite integral by definition I can write as a limit as n goes to infinity of a sum from I equal 1 to n of f of x sub I times delta x. We're going to assume here that we have subintervals of equal width, so there's no subscript I on that delta x. And so when I solve these problems, what I generally try to do is to start by trying to identify that delta x, the width of each subinterval. And I remember that delta x is b minus a divided by n. So a is the lower bound, b is the upper bound, n is the number of subintervals. And then what I'm looking for, and this is perhaps the hardest part, I'm looking for a function that is evaluated at x sub I, which is equal to the left-hand endpoint, plus I times that value delta x, the width of each subinterval. In my opinion, that's the hardest part to do here, is to try to identify that function correctly. And then once we do that, the a and the b sort of fall out from this. We can find b by looking at, well, we start at a and we add, well, n times b minus a divided by n. And when that happens, the n's cancel. We're left with a minus a, and we know what b is. Well, let me try to apply this kind of weird way of doing this to this first problem. Let's take a look at this limit of this giant sum. As I stare at that, I can see, I think I can convince you that delta x here, the width of each subinterval, is equal to 5 divided by n. So that's my b minus a divided by n. Now I have to look for an expression, a function evaluated at at a plus I times delta x. Well, I can see that delta x in there, that 5 divided by n. I can see the I times delta x. And here's a 4 plus that. So it's looking like this a plus I times delta x is equal to 4 plus I times 5 divided by n. So it sure looks like a function evaluated at x sub I is the square root of x. So let's see. If this is my x sub I here, that 4 has got to be the value of a. What's the value of b? Well, I'm going to start at 4, and I'm going to plug in an n over here, because these are actually right Riemann sums. I'm going to plug in a value of n for I, so 4 plus n times 5 over n, and that's 9. That's my value of b. So I've identified the delta x. I've used a little bit of calculus vision here to find a function, to see a function evaluated at x sub I. That helps me identify the left hand and the right hand endpoint. So my function is simply the square root of x here. The definite integral is from 4 to 9 of the square root of x dx. That's pretty cool. Let's try one more. All right, this one's a little bit trickier. I can look at this, I think, quickly and see, well, you know what? That's got to be the delta x. So, okay, delta x here is 4 divided by n, which once again, I'll remind myself is b minus a divided by n. And now I've got to look for an expression that looks like a plus I times delta x. You might be tempted here to think that that a is this 1. But this isn't a or 1 plus I times delta x, because look, this expression is squared. So it's not of the right form. So I've got to think about this a little bit more. What sort of function do I have evaluated here at an a plus delta x? Well, this function is looking like 1 divided by 1 plus something squared here. And inside there, I really have an x sub I equal to 0 plus I times 4 divided by n. And that whole thing is going to be squared. There's my x sub I inside those parentheses. So how does x sub I, how does this vary? Well, it starts at 0. And when I is equal to n, it goes to 4. So I think I've evaluated, or pardon me, I found that a is equal to 0. I found that b is equal to 4. And what does this function look like? Well, it's 1 divided by 1 plus this x sub I squared. So it becomes that definite integral. That's kind of a neat one. Have to think a little bit about that to figure out, to really see what that function is. Cool. I'm going to try one more anyway, Curtis. I think we've got time for one more and maybe an overtime problem. So this is kind of a typical sort of a problem. I've got many more parts here, I think, than you might see on an AP calculus exam. But this function is defined, f is defined on this interval 0 to 10. And it has 3 straight line segments and a semicircle, as shown in this figure. And I simply want to use this graph to evaluate each one of these definite integrals. Now, I may not do all of these, but let's take a look at some of them. And Curtis, I may need a little help here. Okay. 0 to 2, f of x dx. My graph is going to get a little bit messy here. I want to evaluate from 0 to 2. And in order to evaluate this definite integral, one mistake that some students make on these kinds of problems is they actually try to come up with an analytic expression for f. and actually try to find an antiderivative and then evaluate at the upper bound, subtract what you get from the lower bound. So they actually try to apply the fundamental theorem of calculus to this problem. But in this type of problem, I believe what they want us to do is to understand that the definite integral is really an area.
Yep.
It represents an area. So from 0 to 2 f of x dx, we've actually got to find the area underneath that curve, but it's negative because we're going to attach a negative sign to that calculation because it's below the x-axis.
Yep.
So the area of the triangle is 1/2 the base, which is 2 times the height, which is 4. There's my negative sign. And so I believe that definite integral is simply a -4.
Would agree with that.
All right, good. How about the definite integral from 2 to 6? Well, let's see. From 2 to 6, I've got this semicircle. It's above the x-axis. So the area or the expression, the answer is going to be positive here. So let's see. We know the area of a circle is pi r squared, but wait a minute, we need half of it here. So there's a 1/2 out in front. So it's pi over 2. And what's the radius there? Well, there's the center of the circle. The radius is 2. One of the 2's cancel. And so, yep, that's just 2 pi. I got that one. Pretty cool. And let's use the same graph, but let's throw in a couple properties here of definite integrals. So this one, I want to find the definite integral from 6 to 0 of f of x dx. Now, there are many different ways to get this answer. For me, Curtis, I really like to rewrite this using properties so that the lower bound is, in fact, less than or equal to the upper bound.
Yeah.
So I'm going to switch the order here on these bounds. And when I do that, I have to put a minus sign out in front. And I'm also going to split up this definite integral into 2 parts because over the integral 0 to 2, I have a straight line segment in there. From 2 to 6, I have a semicircle. So 2 sort of different calculations, which thankfully I've already done. So I've got a -4 and a 2 pi, and there's a minus sign out in front of all of that for a 4 minus 2 pi, which is pretty cool. Let me see if I can do 1 or 2 more here. I think I've got some more. If I can arrow up just a little bit. There we go. All right, 6 to 10 of f of x dx. I broke that up into a couple of parts. One reason was because part of it was above the x-axis, part of it was below the x-axis. So a couple of different triangles there. I won't go through all of those calculations. And then finally, I put all of this together and went 0 to 10 f of x dx and used a lot of the information that I computed, a lot of the values I computed in 1 through 4. Here's another one that uses a property of definite integrals. This is 9 to 6. I'm going to flip it and put a negative sign out in front. So that's a nice problem. And let's see, I think I had one more part to this. Oh yeah, this is kind of neat. This is a very typical AP calculus question where we have a graph given of a function f, and we define a new function g as in terms of f as a definite integral from 4 to x, and we want to find the absolute maximum value of g over that interval. Well, the first thing students would need to do here is to recognize we need to use the fundamental theorem of calculus in order to find the critical values. So g prime is really f, and I think it's important for students to write that on the paper. That's often worth just 1 point, recognizing that, using the fundamental theorem of calculus correctly. Often we refer to that as part 1. So where is f 0? If you think back to my graph, let's see, f was 0 at 2, 6, and 9. And although there were some sharp corners in the graph of f, remember that represents the derivative of g, and f existed everywhere on that interval 0 to 10. So in fact, there are no places where the first derivative does not exist. So I need to evaluate this function g at those 5 places, at the endpoints and at the critical values. And I did all of that and using area. And I think after all of that, the absolute maximum, I believe, was at 6. And the answer there was pi, half of that semicircle. That's pretty cool. All right, we had another problem in here, Curtis, that we're not going to go through, but we felt obligated to include. This is kind of a typical problem in many textbooks. Use the strict definition here of a definite integral. Use the limit of a sum to show that in sort of general. That's kind of a nice problem because it makes you think a little bit about what an antiderivative of x might be. At least that's the way I do it in my class. So we put that one in here. We included that, I guess we'll say for completeness. And let me close, Curtis, by taking a look at one of these overtime problems. I really like this one. I actually solved this a little bit differently than what was given on the AP Calculus Facebook page, but I think this is a cool problem that actually uses technology. We have a function f defined like this. It is a polynomial. It's a cubic polynomial. We want to find the derivative of its inverse at 1. Well, when I saw this problem, the very first thing I thought about is, well, wait a minute. I'm not convinced that f even has an inverse. So here is a way that I attacked this. I took a look at the first derivative of f, which was pretty easy to compute because it was a polynomial. I took the derivative term by term, and there's sort of some weird calculations in here, Curtis, but help me. Tell me why I did this. I actually took a look at the discriminant here. This is a quadratic, and it turned out to be negative, and that tells me that there are no real roots. So that says that this function, this first derivative, does not cross the x-axis.
Means it's always positive.
It's always positive or always negative. I don't know that yet. It's always positive or always negative.
You can look at the intercept. The intercept is positive.
Beautiful.
It's always positive.
It's always positive. So that says the first derivative is always positive for all x.
Which means f is increasing.
F is increasing. That means it's 1 to 1.
Yeah.
And that means it has an inverse.
That's pretty shrewd. That's a nice...
very cool. Okay. So that means, for me, that means that I can find this derivative of the inverse by using this formula that we derive usually once we learn a little bit about implicit differentiation. There's generally a problem on the exam that relies upon this formula. Unfortunately, maybe you got to commit this one to memory. Well, wait a minute. If I'm going to use that formula, I got to find f inverse of 1. So that means I need to solve this expression. What value of x returns a 1 in the original function? Well, Curtis, I can't solve that one by eye or analytically, so I had to go to the calculator to find that. And I'll show you that on the TI-Nspire in just a second. And once I found that value, then I find the first derivative, the derivative of f at that value, and there's my answer that I was after, rounded, I think, to 3 decimal places. Here's how I did it with the Nspire. I defined my function f, and I found that value. I found the inverse. I found the value of x right there that returned a 1. And I stored it. I'm getting fancy at this now. I stored it in a list. It's a list that has only 1 entry. I did that so that I could grab that value easily. I evaluated 1 divided by the derivative of f at that value. There's my 0.219. That's really cool. I think that's a neat use of technology. There's some cool theorems and logic going on, I think, in that step. And I just did a little bit with a graph here just to convince myself that, yeah, let's see, that really is the value of x that returns a 1, just justifying that inverse.
Wow.
Well, that's pretty good, Curtis. We had
nice problem, Steve.
We'll post all of those sometime tomorrow. I'll get this to you. Tom, some great technology. Thanks, Curtis. Yeah. Very good.
Yeah, this was great. Thank you, Steve. Thank you, Tom. This was a good session tonight. Good chat in the chat box tonight. I will put my email address here in the chat real quick. Curtis at TI.com. Send me a quick email and I will send you a link for the PD certificate as well as the schedule for the remaining sessions that we have for Monday Night Calculus, as well as invite you to join us for our last pre-calculus live session here in a couple weeks. I'm really excited that we're doing that pre-cal series as well. Spread the news to your AP pre-calculus teachers and just any pre-cal teacher and student. It's good content that Steve and Tom have come up with. All right, we'll see you guys here in a couple of weeks. Enjoy your Thanksgiving.
Thanks, Curtis.
Good night. Right.